They're going to pass their information, so like that name that
Okay, because
Alright. So I'm just going to pass around a paper and a pen, and if you guys are interested in coming in on Friday, please write your names and email address, and I'll then pass the paper. If you're not interested, you're allowed to. Oh, and also apparently pass this around too.
If you haven't got a chance to register, just fill out that form and just leave it around afterwards.
does the registration on the website or?
You can do it on the website, but I know.
But like just that's the same registration?
Yeah.
Okay.
So, I assume everyone can read this.
Yeah.
Is my sound working again? I can't hear it. Okay. I assume everyone can read this. If anyone can, like, I think I've got my own web address right, but I don't type it in very often, so you know, someone might want to check that. It's some the problem is every place I go, I get a different combination of letters. So when I was in Alberta, I was AM Tomps, and now I'm A Thompso. And in Oxford, I was A Thompson. So it's like, really, come up with like, can't I just give you a set of letters or something, you know?
An 8-letter name, and it's like, you know, I think we've got some figured allowed all with an 8 character.
If they all went with A Thompson, that'd be fine, or AM Thompson. It's just like, it's always 8 characters, but it's like an arbitrary different set. Okay. So I'm just moaning about web addresses. Don't worry, I haven't started talking.
The people who are coming to the lectures should register online for the program so that we know who are here, right? And also the U of T grad student now, of course, is, you know, you can take as a credit. So you should fill out the form. I just circulated to you. And then Alex, not Alex, Simon has an announcement.
Yeah, so there's a piece of paper that's there going around. If you are interested in dinner tomorrow night, please add your name and email address. If you're not interested, you don't have to write anything on the form. But if you are, please write it down so we have a good idea who's going to be there, so that we can make appropriate reservations.
Okay, so the second talk of this morning is Moduli of K3 surfaces by A. Thompson.
Yeah, so there are full notes for this talk online on my website. I hope that this is the correct address. That'll take you straight to the talks page, and this one should be the top one. So if you can't be bothered to write anything, you can get literally everything I'm going to say from there. Everything I'm going to say is contained in more detail in 2 references. The 2 references are Barth, Hulek, Peters, van der Ven, complex surfaces, which Ursula mentioned earlier. It's a very, very comprehensive book, which is also completely riddled with typos. So yeah, there's every time I read it, I find more mistakes. It's kind of amazing. The second one is Francesco Scottoni, which I think this was like a publication of his thesis on the compactification of moduli spaces for algebraic K3 surfaces. So some of the stuff I'm going to say about algebraic K3 surfaces and some of the stuff I'm going to say about degenerations and compactification is contained in there. But between the 2 references, you can get pretty much everything. Okay, so let's get cracking. Okay, so let's start off by remembering something that Ursula said. The Hodge diamond for a K3 surface. Oh, I should have said. Let's say a K3 surface, surface X. So X is always going to be a K3 surface in this talk. I'm not going to keep saying a K3 surface. And it looks like the following. We have 1, 0, 0, 1, 21, 0, 0, 1. Okay, now, what are we seeing from this? Okay, so everything interesting. happens in H2. So, you know, I mean, all we've got one dimension in H1, nothing, one dimension in H0, nothing in H1, nothing in H3, one dimension in H4. So, you know, H2 is really where the action is happening here. Actually, I should have said at the start, if you were here a couple of weeks ago and you were watching the talks, most of what I'm going to say was actually contained in the talks by Klaus Hulek, who literally wrote the book, and Radu Laza. But I'm going to sort of do some sort of combined amalgamation of some things that they said and maybe a couple of other things. Okay, so everything interesting is happening in H2. So what do we, well, what's the aim of the first part of this talk? Use the structure of H2 to study the moduli of K3 surfaces. I've got to press less hard. This is really soft chalk. Okay. Okay, so let's talk about this structure. So H2xz, the integral cohomology, is isometric so this is something that Ursula mentioned, and is isometric to the K3 lattice. And I'll tell you what the K3 lattice is. Stop. Seriously. Okay, so the K3 lattice lambda K3, this is H direct sum H, direct sum H, direct sum E8, direct sum E8. So this is what this thing is as a lattice. I'll tell you what each of these symbols mean in case you're, I mean, well, it's not completely standard. So H is an even unimodular, indefinite lattice of rank 2. And by convention, I'm saying that E8 is an even unimodular. So I'm using the opposite to the standard definition. I'm going to say it's negative definite. Negative definite lattice of rank 8. That chalk's dead. Let's find one of reasonable size. Of rank 8, corresponding to the E8 thinking diagram, corresponding to the E8 diagram. Okay. Okay, so whatever K3 surface X you pick, its second integral cohomology is always going to be isometric to this lattice. And I should say, actually, lambda K3 has rank 22 and signature 319. Okay. Okay. Do I need to send that up? Can people see it? Okay. Okay, so what do we get from all of this? Well, the first theorem we get, which again was mentioned by Ursula, is the weak Torelli theorem. And the weak Torelli theorem is sort of our first step towards using this information to construct a moduli space for K3 surfaces. So here is the weak Torelli theorem. Okay, so 2 K3s, X and X prime, are isomorphic if and only if there is a lattice isometry from obviously H2xz to H2x prime z that preserves the Hodge decomposition. Okay, and such isometries, this is going to be called a Hodge isometry, so we're going to come back to these. These will be important later. Okay, so this is a Hodge isometry. Okay, so that's kind of all well and good. Well, okay. I mean, technically what I mean here is that, you know, the C linear extension of this preserves the Hodge decomposition, but you get my point. Okay. Okay, are we good so far? Okay, let's talk about the period map. Okay. Okay, so in order to start using this to define a moduli space, we're going to have to define what's called a marking on X. So this was the map phi that Ursula used that Noriko asked a question about. So I'm sort of this talk maybe would have made more sense going before Ursula's, but we didn't really know what each other were going to talk about. So okay, so a marking on X is a choice of isometry phi, which maps from, which way does it go? H2xz to the K3 lattice. So in general, a K3 surface will admit many different markings. And yeah, so in order to get a good moduli space, we've somehow got to sort of kill the automorphisms, which we do by choosing a marking. And we're still not going to get a particularly good moduli space. We'll see that in a second. Okay, okay, now where do I want to go? Let's go up there. Okay. Is it always that bad? Man. Yeah, I know, that one's pretty dire. Well, I'll use this one next time. Maybe if I leave it upside down, it won't get so much chalk on it. Okay, so okay, let's let omega in H20 X be any class. So H20 is one-dimensional, so it doesn't really matter what, well, when I say any, I mean I should say any non-zero class, but you know, if I pick any omega in H20, it's always going to be the same up to scaling. Then if I have the inner product, the inner product of omega with itself is 0, and the inner product of omega with its complex conjugate is strictly greater than 0. These are just sort of lattice theoretic facts. So where am I going? So if phi is any marking, for X, and let's say phi sub C is the compactification of phi, complexification of phi, sorry. Then phi sub C of H20 of X defines a point in, so well, I mean, okay, we'll see. So if I apply phi sub c to H20 by the fact that this omega and omega bar have this property, oh, I should have rubbed that one off. Oh well. Too late now. I should be sending them up as I do them rather than afterwards. Let's do that now. Send that up and bring that down. Then I won't get confused. Okay. Okay, so phi sub c of H20 is a point in the following space. Omega K3, which is defined as the set of the class of omega in the projectivization of lambda K3 tensored with C, such that, so I mean, this is why, you know, our one-dimensional thing H20 can map to a point, because we're taking this projectivization, and we get the inner product of omega with itself is 0, and the inner product of omega with omega bar is strictly greater than 0. So anything that we, I mean, our H20 is going to have to map into here by the properties we put up on the board before. So what is this thing? Omega K3 is a 20-dimensional quasi-projective variety. I mean, really, it's just some sort of open set of a locus defined, vanishing locus defined by a quadratic equation in a 21-dimensional space, I think, something like that anyway. And it's called the period space of K3 surfaces. Called the period space of K3 surfaces. And the point defined, let's see if I can fit it on here. The point defined by phi c of H20 of x is the period point of x. Let's say the period point of x phi, because it depends on the marking as well. So, okay, so okay, so this has sort of set up a bit of theory for us. Now let's see what we can get from this. You should go up, you should come down. Okay, so we've got two theorems coming up that concern this thing. We've got the first one is another version of the Torelli theorem. So this is called local Torelli. And this says that the map from the versal deformation space of x to omega K3 is a local isomorphism. Okay, so this is starting to make it look like, you know, omega has something to do with the moduli space of K3 surfaces. And the second theorem we're going to have is called surjectivity. surjectivity of the period map, which does exactly what it says on the tin. It says that the period map is surjective, basically. Every point of omega K3 is the period point of some marked K3 surface. Okay. Okay. Where am I going next? Am I getting some sort of interference off this thing? Is it hitting my... Is it hitting my jumper or something? I don't know. Okay. Oh dear. I don't know what's causing that. That's only happening for me. I think maybe it's bumping into my face. Let's try bending out a bit. Okay, no, that's not working. Okay. So, add on to this the fact that weak Torelli, which I think I've already removed, maybe, maybe not. Yeah, probably. Okay. Weak Torelli, what does weak Torelli tell us? This says that 2 K3s are isomorphic if and only if there exist markings for them so that the corresponding period points are the same. Okay, so, you know, we sort of, if you put all of this stuff together, we seem to be really close to having a moduli space for K3 surfaces. But unfortunately, this is not going to work very nicely, so. So, what do we want to do? To get a moduli space for K3s, we want to quotient. Now, what do we want to quotient? A group that identifies period points corresponding to isomorphic K3s. Dead chalk. However, there's a problem with doing this, and the problem with doing this is that this group does not act properly discontinuously. So in particular, what happens, so the resulting space, is not Hausdorff, which is pretty terrible, to be honest. I mean, you know, if if you want to name properties that you want a topological space to have, then Hausdorff is pretty high up the list. So somehow we failed at the last hurdle. We attempted to construct a moduli space for K3 surfaces, and we got right down to the crunch, and when we got there, we found out that the space we constructed was not very good. Okay, are there any questions so far? Are we still happy? Okay.
Also, deformation and globally discontinuous.
I don't particularly want to go into it if I can avoid it. So, I mean, versal deformation is somehow like all possible deformations, but not quite all possible deformations. And yeah, properly discontinuously means that, I mean, it's sort of somehow you don't have any sort of orbits which look like, continuous curves. You just end up with like discrete points knocking around. At least this is my sort of my intuitive sort of intuitive idea of these things. It's okay. So I mean, yeah, somehow the local Torelli theorem is saying that any way you deform your K3 surface is sort of represented. I mean, any way you sort of locally deform your K3 surface is represented by movement of the period point around. Okay, so in order to fix this, we're going to abandon the idea of having a moduli space for all possible K3 surfaces, and instead we're going to consider a moduli space for a certain subclass of K3 surfaces. So this is polarizations. So what we're going to do is we're going to put polarizations on our K3 surfaces, and this will fix our problem. Okay, so here is a definition. A pseudo-polarized K3 surface. I've put pseudo in brackets. Of degree 2k. Is, how do I want to phrase this? A pair XH consisting of a K3 surface X and a pseudo-ample class pseudo-ample class H in H2XZ. Is there any more to this? Oh yeah, I have to give you what the square is. With H dot H has to be equal to 2k. So it's fairly easy to show that if you have any, I mean, it's just an exercise in the genus formula. That if you have any divisor on a K, if you have any ample divisor on a K3 surface X, it has to have square divisible by 2. So, in fact, I think any divisor at all on a K3 surface has to have square divisible by 2. So we're sort of, somehow we're not missing anything here. If we have any K3 surface that contains an ample divisor, then we're going to get it by this thing. We just pick an ample divisor on there, and then off we go. So this is going to give us. I mean, somehow we're restricting from the class of analytic K3 surfaces down to K3 surfaces which are projective, which makes everything a bit nicer. That's what's going to solve our problems. Okay. So what's the advantage of doing this? Well, we get a better version. We get a better version of the Torelli theorem. And this effectively is what gets. I mean, this better version of the Torelli theorem is what gets rid of this not properly discontinuous thing. So here is a theorem and the theorem is called strong Torelli. Okay. Okay, so let's let x h and x prime h prime be two pseudo-polarized K3 surfaces. Also, for those of you who like the minimal model program, pseudo-ample is the same as nef and big. Okay, two pseudo-polarized K3 surfaces, and then we're going to say, assume there exists a polarized assume there exists a Hodge isometry and again I've got to get this the right way around. Let's say phi mapping from H to x prime first, x prime z to H2 xz, that, oh, let's say such that okay, such that phi of h prime is equal to h. So this map has got to map the polarization on one side to the polarization on the other side. Then there exists a unique, and the uniqueness is important, isomorphism F mapping, oh, why have I used S's there? That needs to be corrected. X to X prime with let's say phi equals F upper star. Okay. Okay, so this somehow is the theorem which is going to solve all of our problems. This is going to make sure that this group acts properly discontinuously. So, and then our space will be good. Okay, next piece of paper. Okay, so what are we going to do? Well, you know, now we have the strong Torelli theorem. We're going to go and we're just going to sort of run the whole construction through again. So now let's say construct a period space for pseudo-polarized K3 surfaces. And that's what we're going to do next. And the construction is going to run in very much the same way as it did before. Okay, so let's fix once and for all a primitive h in lambda K3 with h squared equals 2k. So, you know, I'm picking some integer k greater than 0. I should have said k is greater than 0 here, but anyway. I mean, I guess that's fairly obvious if it's ample. So I'm fixing once and for all a primitive h in my K3 lattice with h squared positive. And then I'm saying then a marked pseudo-ample, let's put pseudo in brackets, polarized K3 surface. They really should have come up with some shorter names for these things. Of degree 2k is a marked K3 surface x phi such that if I pull h back by phi, so if I do phi inverse of h, is pseudo-ample. Okay, so what does this do? Well, effectively, you know, if we pull back this distinguished class H, then we get a pseudo-ample divisor on X. So this defines a polarization on X. So our pair is both marked and polarized. Okay. So in the same way as before, we'll construct our period space. Ow! Ah, crap! That really flipping hurt. Note to self: don't punch the boards. Oh man. Okay. So let's say if x phi is a marked pseudo-ample, etc. Can't bother to write all that out again. A marked pseudo-ample K3 surface of degree 2 or 2k, and omega is in H20 of x. Then, well, of course, from before we had the two relations. The inner product of omega with itself is 0. The inner product of omega with its complex conjugate is greater than 0. But this time we also have this special class H. So what happens when we take the inner product of omega with H? Well, it turns out that's equal to 0 as well. So thus, what do we do? So the period point of x phi lies in the following space, and it's going to look very much like the period space for K3 lattices. Omega in the projectivization of lambda K3 tensor C, such that omega is equal to 0, omega bar is greater than 0, and omega H is equal to 0 as well. Okay, so this thing is going to be our period space for marked pseudo-ample polarized K3 surface of degree 2. I think this chalk is dead. Okay, so omega 2k is the period space of pseudo-polarized K3 surfaces of degree 2k. Of pseudo-polarized K3s of degree 2k. Okay, I should probably say we've got an extra condition, so it's a 19-dimensional quasi Thank you. Quasi-projective variety. Projective variety. Okay, so, you know, previously we had this 20-dimensional space, and now we've got this 19-dimensional thing which sits inside it, wherever I put it up there, which sits inside it as a hyperplane. And there's one of these for every value of k, so there are these sort of countably many 19-dimensional hyperplanes sitting inside this bigger 20-dimensional space. And the important thing here is that if we now try and do this quotient, so if I let gamma of h be the group of isometries of lambda k3 that fix h, then gamma of h acts properly discontinuously, so this is going to solve our problem. And this is a consequence of the strong Torelli theorem. Acts properly discontinuously on omega 2k. Okay. Okay, so combining, you know, this along this, which comes from strong Torelli, along with the surjectivity of the period map, then we're going to finally get what we actually want. We are going to finally get what we actually want. Which is a theorem which was proved by many, many people over a very long period of time. The quotient F2k, which is going to be defined to be equal to the quotient of omega 2k by the action of gamma of h, is the, I should probably say here, coarse moduli space for pseudo-polarized K3 surfaces K3s of degree 2k. Okay. Okay. Oh, we're not doing too badly for time. And I can tell you some things about F2k as well while I'm at it. F2k is a 19-dimensional quasi-projective variety. I think showing it's quasi-projective is actually quite non-trivial. Quasi-projective variety of with only finite quotient singularities. So it's quite nice. With only finite quotient singularities, and something which you don't really need to worry too much about, but which will prove to be, you know, I might mention again if I get round to that point, which I may or may not do depending on how time is going. So F2k can be seen as a quotient of a 19-dimensional bounded symmetric domain. Bounded symmetric domain. And furthermore, it's a bounded symmetric domain of type 4 by an arithmetic group. And, or, well, okay, I say, well, arithmetically defined discrete group of automorphisms is the correct way of saying it. Okay. But anyway, somehow the important thing to take away from this sentence, if you don't know what any of these words mean, is that it's nice. And that niceness is going to be fairly important to us. Okay, so that concludes the first half of the talk in 45 minutes. Does anyone have any questions? Or are we all happy? I'm guessing from the really bored looks in the audience, most people have seen this before, which is kind of a shame. I was hoping there'd be lots of sort of fresh-faced grad students who don't know anything about K3 surfaces, but most of the people out there are all pros. Which means I have to be sort of careful. You're not a fresh-faced graduate, though. You're a wizened graduate. You've been at it for a while now. Okay, where was I? Okay, so let's talk about degenerations. So this is really, you know, somehow all of this was really a build-up. Degenerations is what I'm really interested in from this sort of subject. So what we really are interested in is, you know, what happens when we go. I mean, this boundary is this moduli space is quasi-projective, and it's got some sort of open boundary. And the question is, well, what happens if we, you know, take some family that wanders off in the direction of that boundary? You know, what's going to happen to us? So I'm going to define a degeneration. A degeneration of K3 surfaces is a proper, there's about 15 qualifiers here, proper flat surjective morphism. Proper flat surjective morphism pi, mapping from, I'm going to call the family curly X to delta from a smooth threefold X, from a smooth threefold curly X to the unit disk, whose general fiber xt for t in delta less 0 is a smooth K3 surface. Is a smooth K3. Okay. Now there's an important point of note here, which is actually going to prove quite important for the thing I say immediately afterwards. The thing I say immediately afterwards, so remark, we do not assume X is algebraic. So X could very well be an analytic threefold, but one technical condition we do put on is we do assume the components of X naught, which is pi inverse of 0, are all Kähler. So I don't know anything about what happens if you don't have this assumption. It sort of seems something that everyone works under. So, but the fact that X can be not algebraic is kind of important, because what I'm about to say now completely fails if you assume algebraicity. And this is all to do with the minimal model program in 3 dimensions being fiddly and unpleasant. Which, yeah, well, okay, so that's not a real letter. After a base change, so we can pull back delta to a double or a multiple cover of delta ramified over the origin. After a base change and a birational modification, and this birational modification only affects the central fiber, we may assume pi from x to delta is semi-stable. Now, what do I mean by semi-stable? I mean, i.e., x is smooth. Well, we already know that. X is smooth, and x naught is x naught reduced. That's the word I was looking for. X naught is a reduced divisor with normal crossings. Now, note again here, I don't assume simple normal crossings, because that makes the next thing break as well. Okay, so this is what semi-stable means in my context. I mean that x naught is a reduced divisor and x naught has normal crossings. Okay. Okay, now, let's go to the next board. Some of these are much heavier than others. Okay, so after a further birational modification, we may assume, and this is the bit that you really need only normal crossings and not simple normal crossings, and the x naught being, or x being not possibly non-algebraic, we may assume that the canonical bundle omega x is trivial. And this is, I think, the Kulikov-Pearson-Pinkham theorem, which was finally proved in a book by Pearson and Pinkham, and the proof is long and quite analytic. So, okay, so the resulting degeneration is called a Kulikov model. Okay, so a Kulikov model is one which is, you know, a degeneration by that definition, which is up there, which is semi-stable and which has trivial canonical bundle. Let's just use both hands. Okay. Okay, now the reason that we did all of this work is because there sort of exists a coarse classification for Kulikov models, which means that, you know, you can actually say something about them, you can say something about their central fibers, and this is useful for purposes of studying compactifications, although we're not going to get that far because I think I'm going to run out of time. But, you know, you'll have to believe me. So here is the theorem. So let's let pi from x to delta be a Kulikov model. Then what's true? Well, one of the following cases, I should say then either. So one of the following cases holds. So we have type 1, And type 1 says that X naught is a smooth K3. That's kind of the most boring thing that can possibly happen. I mean, you just have a family and the central fiber is actually just something smooth. Type 2, which is the nice friendly one, is X naught is a chain of elliptic ruled surfaces with rational surfaces at each end. At each end, and all double curves. So double curves are where components meet, are smooth and elliptic. Okay, so I can draw a little picture of this. We have something which looks like this, and so on down. So we have some sort of chain of surfaces. Now, this top one here and the bottom one, these two down here, these are both rational. These three ones in the middle here, like this one, and this one, these are elliptic ruled. Elliptic ruled. And all of these curves that I've joined them together, these are all elliptic curves. So this is type 2. And finally, the one that everyone hates, because it's so, oh man. These boards are destroying my fingers. I hope that's not, oh well. Okay, finally type 3. That's a bad 3. Type 3, X naught consists of rational surfaces meeting along rational curves that form cycles in each component. And furthermore, we can say if gamma is the dual graph of X naught, then gamma is a tiling of the sphere, or is a triangulation of the sphere even. Even better than that. Gamma is a triangulation of the sphere S2. So these are things that somehow look like soccer balls. I mean, you have all of these components, and in each of the components you get like a little cycle of rational curves where it meets all the other components, and when you put all of them together you get something that looks kind of like a sphere. And I'm not going to try and draw one because my drawing skills are not that good, but I suppose you could think of like, I mean, a really easy example is something like a tetrahedron, where all of the faces of the tetrahedron are rational surfaces, and in each rational surface you get the three double curves form a circle. So. Okay, so I guess the last thing that I'm going to say here, because I'm not going to get on to compactifications, which I wasn't going to say a lot about anyway, but if you want to know about them, you can read about them on the interweb, on this set of notes that I've written. Or alternatively, if anyone's interested, I've got some sort of insightful and useful problems that I've dug up that, you know, if anyone wants to come and do some problems this afternoon, we can, you know, calculate some degenerations and, you know, derive some basic properties of K3 surfaces and that kind of stuff. It'll be good fun. You know, things like showing Kulikov models are not unique and all of that kind of junk. This is kind of cool. So I'll just say a remark. These cases can be distinguished without actually looking at the central fiber at all, by the action of monodromy, on, again, our old friend H2 XTZ, where XT is just a generic fiber. So let me tell you how this works. So let's let T be the transformation induced by monodromy, or induced on H2 XTZ by monodromy. And let's let n be equal to log t. Okay, so we're letting n be the logarithm of t. Then it can be shown that n is nilpotent and we can use, you can detect from the nilpotency of n, you can detect which of the three cases we're going to be living in. So and let's say if n equals 0, so if n is just trivial, x naught is type 1. Secondly, if n squared equals 0, but n is not equal to 0, x naught is type 2. And thirdly, if n cubed equals 0, but n squared is non-zero, x naught is type 3. And one can show that you can't get any more cases. The third power is the highest. I mean, n cubed is always going to vanish. That's what I'm looking for. Okay, I think that's it. So as I said, if anyone's interested this afternoon, I do have some sort of fun calculations where you can get your hands dirty and play around with some of this stuff. So yeah, sort of find me after lunch, and we can do that if anyone's interested. The notes are already online on my website, which I mentioned at the start. I can give you the address again if you want. Alternatively, if you search Google for Alan Thompson math, then you will find me. I think I'm the only Alan Thompson doing math. If you just search for Alan Thompson, you won't get me in the first 10 pages. There's a soccer player in Scotland who has the same name and the same spelling as me, and he has hundreds of fan sites. And you know, he's far more well known to the general member of the public than I am, so he gets all the hits.
More questions? No, then come to the speaker. If the graduate students from U of T, if you want to register for credit, it will give you some problems to work.
I wonder if my girlfriend tuned in. She said she might do. I'll get a text message now, like immediately. Yes, I'm here. I'm watching you. She's not a mathematician. She just wondered like what it is I do.
She kind of thinks she doesn't understand anything about it.
Well, the thing is, she'll be at work anyway, so she like have it open in the background of her computer while she sits there with us. She can make her coding transparent, so she can watch the video through it.
I don't know if that would be a good way to do it. Maybe you're getting motivated if you're watching something you care about. I probably watch the video. Yeah, I get it.
Yes. Oh yeah. No, John was like a sweaty.
Yeah. I don't know if I saw that.
Yeah, a jump was just like This is, now all of this is not technically quite tedious, it's got buttons on it. Sort of halfway between the three.
This is not.